Hello, everybody. Welcome to lecture 2. All right. Let me start with a remark. So let's consider now this problem: y tilde t ct equal alpha Laplace of y tilde ct plus f t y tilde ct with ct in omega 0 t y tilde c 0 equal y 0 c this is equal y 0 y, so at the boundary so this is when c belongs to the border omega times 0 t, and omega in this case is a subset of R2, and y tilde is a function from omega 0 t in R2. So now we have a two-dimensional PDE. Again, we have a parabolic PDE. Alpha is a real number. We have a nonlinear term. So if we use finite difference, we will get something of the form that was discussed in the previous lecture, plus initial condition. What is now the big difference is that the matrix D now is very large. I mean, usually for a two-dimensional problem, the dimension of the problem is way larger than the dimension of a one-dimensional PDE. I mean, the higher the dimension of the PDE, the higher the dimension of the discretized problem. Nevertheless, we always get something in this form, which is our problem setting. In the lecture notes, you will find details for finite difference schemes for 1 and 2 dimensional PDEs, and also you will find MATLAB code to approximate those PDEs. I suggest you guys to also to take a look at the notes, and in particular also at the code, and try to, I mean, this is a simple cut and paste of what it's written. I mean, we have to probably put some few things, but you should already be able to run the code, the simulations. Also, I have provided just one example, one PDE example, but you are free to choose your F, or also to modify, try to put an advection term instead of a Laplacian term, or let's say something which is advection plus diffusion plus a nonlinearity, something like Burgers. I mean, just I would say that it's nice and it's interesting if you play around and if you get something out of this code. Okay. Again, I want to rewrite my reference problem. So it's d-dimensional ODE. So this is a system of ODEs with D equations. Okay. So the main idea of model order reduction is to project this problem onto a low dimensional one. Using orthogonal projections. Okay. So let us suppose that now let us consider a fixed matrix psi dimension D times L. D is the dimension of the original problem, and L should be way smaller than D. So the columns, I will denote the columns of psi, psi1, psi L, such that the columns of psi are orthonormal. In other words, Ci transpose Cj are equal delta Ij, which means 1 if I equal j, 0 if I is different from j. And Ij goes from 1 to L. So we define the space spanned by C1, CL, which is so C1, CL are basis for the subspace, the L-dimensional subspace of RD. Then we suppose that our solution y of t belongs to VL. In other words, that means to suppose that y of t can be written is approximate something which is psi YL of t, where, so let's write that again. So Y of t can be approximate by using Y times YL of t, where YL of t is a function from 0 t to RL. In this case, C, this is given. We will see how to get C. At the moment, we suppose that this is given, and YL, this is unknown. That's something that we want to compute. What's the main difference here? So YL is now a vector in our L with L way smaller than D. So the key fact is that we suppose that our solution lives in a low dimensional subspace whose dimension is way smaller than the original dimension. That's our assumption. And if we plug Y of t psi YL of t into our reference problem, we obtain so remember that my reference problem is my dot ay plus f. So we obtain m psi YL of t equal a psi, this is y dot YL of t plus f t psi YL of t. And then we have that psi YL of 0, this should be equal to y0. There is an important fact here that I haven't mentioned, is that if I compute psi transpose psi, this is equal to the identity in the dimension L. L by L. This is just a straight forward consequence by the fact that psi is given by orthonormal vectors. So now we have this problem. If we multiply by psi transpose on the left, we obtain psi transpose m psi y dot L of t equal psi transpose a psi YL t plus psi transpose f t psi YL of t And also we will get something like okay. Then we also get that psi transpose psi YL of 0 is equal to psi transpose Y0. So let's take a look at the matrix psi transpose M psi. So the matrix psi transpose, so this is psi transpose, this is L by D. The matrix M is a matrix D by D, and the matrix C is a matrix D by L. So where does this matrix live? This is a matrix L by L. So now here we have an L-dimensional matrix, which I'm going to call ML, and is defined as psi transpose M psi. Let's take a look as well at the matrix psi transpose A psi. This is the same because we have an L by D matrix, D by D, D by L. This is L by L. And again, I'm going to denote AL. This is the projection onto this basis, right? Of the matrix A. Here we know that this is the identity psi transpose psi, and C transpose Y0. This is L by D, D by 1, right? So this is a vector dimension L. I'm going to denote by Y0L C transpose Y0. Okay. So in other words, what we have here, we have ML Y dot of T equal AL Y of T plus psi transpose F of T psi YL of T. This is YL. And then we have YL of 0 equal Y0L. What is the main feature here? So now we have L-dimensional system of ODEs. So we started with an infinite dimensional problem. Say a PDE. We make a semi-discretization in space, which provides a d-dimensional system of ODEs, D large, Yeah, I keep stressing the fact that we are working in a very large dimensional, for a very large dimensional problem. And then we make a projection to reduce the dimension of the problem. So what we have is that L is way smaller than D. All right. So at the moment, I keep some suspense. I do not explain how to compute psi. That will be in the next lecture. But what I want to stress is that actually, maybe I make a remark. When we multiply by psi transpose on the left, this is a Galerkin projection. So that means that we want to ensure orthogonality with respect to the residual. The residual will be time dependent for sure. So one can also try to do a Petrov-Galerkin projection, but this is out of the scope of the notes. In particular, for the method that I'm going to explain, which is proper orthogonal decomposition, we are not going to use Petrov-Galerkin approximation. All right. So suppose we are able suppose that we are able to find the matrix C, and we get ML y dot L equal AL YL T plus psi transpose F T psi YL of T, YL of 0 is equal Y0 L. So suppose that we are able to find the matrix psi. So we make the projection. We have this low dimensional problem, and now we want to approximate and compute YL. How can we obtain YL of T? This is rather simple. I mean, if you see this problem, I mean, the structure of this problem is exactly the same of the high dimensional problem. The only difference, I mean, formerly we had the same problem. The only difference is due to the fact that we have a low dimensional problem. So we can use implicit scheme. To approximate this problem, but as you will see, the code that I've developed, that I provided in the notes, is exactly the same. I just have to change the function that I want to solve. Now this is going to be a little bit different. All right. Then I think it's a good moment to talk about singular value decomposition. Okay. Let's start. Okay. Let y a matrix D by M with rank R less or equal M and D greater than M. Let psi given by psi I which goes from 1 to D. This is not D. And then we have V, which is going to be I1 to M, not M. B, the set of orthogonal vectors such that y vi is equal to sigma I ci and y transpose ci is equal to sigma I vi. E goes from 1 to R. Then sigma 1, sigma R sigma 1, sigma R are called singular values and psi V are called psi I vi are called left and right singular vectors. Okay. So we suppose that we have a matrix, a D by M matrix, and there exists something which is so two vectors, two pairs of orthonormal vectors, so psi that are orthonormal and vi that are orthonormal, such that y vi is equal to sigma I psi and y transpose psi is equal to sigma I vi. So sigma I are the singular values, and psi and vi are called the left and right singular vectors. Let's provide a theorem. So let y equal y1 yd ym be a given matrix with real value d by m of rank r less or equal the minimum between d and m, then there exists a singular value decomposition which from now on is going to be SVD with real numbers sigma 1 greater than sigma 2 greater or equal sigma r, which is strictly positive, and orthogonal matrices psi equal psi 1 psi d, which is a d by d matrix, and v equal v1 vm, which is a m by m matrix, such that y can be decomposed as psi sigma p transpose, where sigma is equal to diagonal matrix 0 0 0 d by m, and d is a diagonal matrix with singular values. So we always have this kind of decomposition. I think it's important. So the name is singular value decomposition. So we have an important thing is that the singular values are positive and they have an order. Furthermore, the matrix sigma is given by a diagonal matrix, which is going to be r by r with all the positive singular values, and then zeros in the matrix. So this is about the existence of this decomposition. Let's also see a lemma. For any matrix y d by m, the singular values are uniquely defined. whereas the singular vectors corresponding to the singular values greater than 0 of multiplicity 1 are unique up to a change of sign, are unique up to a change of the sign. Okay. So in other words, we can always compute this singular value decomposition. And I think it's interesting to see a relation between singular value decomposition and eigenvalues problem. What is very important to note is that the matrix Y can be rectangular. In the case of eigenvalue decomposition, we always deal with a square matrix. Okay, let's see. Let's see what happens if I do. So remember that we have C sigma V transpose. If I compute Y transpose, this is C sigma V transpose V sigma transpose psi transpose. Okay. So since we know that V is orthogonal, V transpose V, this is the identity. So here we have here we have psi sigma transpose psi transpose. Okay, so that means that Y transpose psi is equal to psi sigma transpose. In other words, Y transpose Ci is equal to sigma I square Ci. This is for I equal 1 to R, the rank. Okay, so psi is eigenvector of Y transpose with eigenvalue sigma I. On the other hand, if I compute Y transpose Y, this is equal to V sigma psi transpose psi transpose sigma V transpose. This is the identity. So we have V sigma transpose sigma V transpose, which is equivalent to Y transpose Y V equal V sigma transpose sigma, or Y transpose Y VI sigma I square VI. So VI is eigenvector of y transpose y, and sigma I square is its eigenvalue. So one can think the singular value decomposition as a generalization of the eigenvalue decomposition. One can also define. So what we also know is that if A so usually it is not possible to compute the inverse of unknown square matrix but the SVD allows to compute something which is called the pseudo inverse by Morpher-Rose. So that means if y is given by psi sigma v transpose, I use the notation y plus, where y plus is the standard notation to denote the pseudo inverse. This is defined as V sigma plus psi transpose, where if sigma is given by D0, 0, 0, sigma plus is given by D minus 1, 0, 0, 0. All right. I think this is a good point to stop here. Next lecture, we will see some more properties about the singular value decomposition and how the singular value decomposition can be used to in model order reduction. So again, thanks everybody, and just feel free to contact me if you have any questions. Bye bye.